All right, so whatever or whenever we talk about something being conditional, and we talked about this at the beginning of the year, if you remember if and then statements, they were called conditional statements, right? Because in order for us to come to a conclusion, a certain condition had to be met. So if, let's say, if two angles are vertical, then they are congruent. The only way then, when I'm looking at two angles in that scenario, for me to make the argument that they're congruent was to say that they were vertical. Does that make sense? Okay, establish that condition of verticalness or verticality. I don't know what the right word is. Is the only way that condition needs to be met for me to make the conclusion of congruence. Now, there's other ways that angles can be congruent, but that's one. So today, when we want to arrive at a certain probability, there's going to be a condition that has to be met first that allows us to accurately determine what the probability of the scenario is. Okay, so I'll give you a scenario here. Okay, what we have here is just some business that has sales, or we've documented like the total sales of salespersons in this company, some of which went to a seminar and some of them that did not go to a seminar, okay? And we want to determine, okay, well, what's the probability that sales increased if they went to the seminar versus sales increased if they did not go to the seminar, that kind of thing, okay? So we structure our data this way, okay? So we have two, we call them in statistics, we call them variables, okay? We have attendance as a variable, okay, and we have sales as a variable, okay? So you're going to have a data value, okay, for whether you attended the seminar and had increased sales. You're going to have a data value for did not attend seminar and had increased sales, okay? And those data values are found at the cross section of these. This is referred to as a contingency table. Okay, not necessarily a vocab word that you need to know, but when you get contingency tables, you intersect a row with a column. Does that kind of make sense? Okay, and then so that 48, we know those are the people that had increased sales and they attended the seminar. Okay, the bottom row and the column to the right are always totals. Okay. Sometimes what they'll do with a contingency table is, and you might realize this on the end of course exam at some point, they might say, I'm going to leave that one blank. Maybe I leave that one blank. We can then leave that one blank. We can leave that one blank. And let's leave that one blank. With these four values up here, we should be able to find all the other missing. If I know I should have a total of 50 here, what should that one be? 2. Okay. And now that I filled that one in to be 2, this is a total of these 2. Does that make sense? So that's got to be 20, right? This has got to be 100, correct? If this is 20, this was 100, and this was the total of these two things, and this was 20, doesn't that have to be 80? And then I've got this last one here, can kind of come up with different ways of finding that. I can use this column here, or this row here, or that column there, knowing that this has got to be, you've got to add up to 50, so that's going to be, what, 32? Does that kind of make sense? Okay. That practice of being able to find basically all those value points. Think about this. If I give you, this is a statistical concept, but if I give you an average, and I tell you that I took 5 numbers to find that average, and I'm going to give you 4 of those numbers, okay? Those 4 numbers can be anything they want, okay? But if I know what the average is, there is then one number that is stuck to being what it has to be to make the other 4 add together with it to create the average, okay? That concept is called degrees of freedom in statistics, and that's kind of what's going on here. This table has a degree of freedom of 2, which basically tells me that if I've got 2 of the values up there, I should be able to find the rest of them. Okay, but they might ask you to do that, to fill in a table off of knowing some totals, knowing maybe one of these intersections of increased sales, attendance seminar, or whatever, and you can fill in the rest. Sometimes they give it to you complete. Sometimes you got to work and fill it in before you can get to the probability question. Okay, but here it says find the probability that an individual that had increased sales, given that they attended the seminar. Okay, so if we think about going back to Chapter 2, whenever we try to prove something in Chapter 2 and beyond Chapter 2, after we learn this concept, all our conditional statements throughout the course, when we tried to prove something, we had a given and a prove, right? Okay, and that given matched to the if statement in the theorem, correct? And the prove matched to the then. Okay, so when it says given here, okay, that is your condition. Okay, that's what's got to happen first. Is that okay with everybody? So that's kind of the if part. If this is happening, then let's go ahead and find this probability then if this has already occurred. So when they say the word given that, okay, you are being provided with that information. You already know that information per this scenario, okay? So when I'm being asked that, okay, increased sales, and given that they attended the seminar. So what that allows me to do, if I have the table in front of me, it allows me to just focus now just on this. Okay? Because I know an extra piece of information. I know that they've attended the seminar, so I can narrow my focus. Does that make sense? I'm no longer looking at the total of 100 people. I'm now looking at only these 80 people because I'm being provided extra information that allows me to kind of narrow my focus. Does that make sense to everybody? So when I ask you, okay, what is that probability? It's not 48 out of 100, and that's what a lot of people will say. It's 48 out of 100 because that's 48 in that cell. The total is 100, right? Okay, but because it says given that they attended the seminar, now it's only 48 out of the 80 people that attended the seminar. Does that make sense to everybody? Okay. Now, I just think it makes a little bit more sense the way I've written. You see I kind of blocked out some numbers here. If I were to erase those numbers, and if you printed this off, they're as decimals. There's like 0.48, 0.32, and 0.8. I think it's easier the first time we see one of these questions to deal with them as, you know, there was 48 people here. There were 32 people, 80 people. So when I say 0.48, 0.32, and 0.8, you don't know how many people that is. Does that make sense? They're all percentages. It could be 1,000 people. So for 0.48 would be 480 people. Does that make sense? So I think it's nicer to look at kind of the raw data instead of as decimals. Okay. Okay. So because in order to figure this out, then the probability, the way we write this, the probability of increased, I'm going to write it in words first, increased sales given they attended the seminar, that's going to be for us, will be 48 divided by 80. Change that to a decimal, you've got your probability, right? Okay. This is what we refer to as the conditional probability formula. This is the notation that we're going to see. Okay. This symbol right there is shorthand for the phrase given that. Okay. A lot of times mathematicians, when writing things, we like to be concise. We don't want to write out full sentences inside those parentheses. So we have the probability of increased sales. We say a vertical bar, so we read that as given that they attended the seminar. And what we're finding out there, think about what that numerator looks like, okay? That numerator is that they attended the seminar and had increased sales. Okay, because that was the intersection of that row in this column, right? So this 48 right here, those 48 people met both conditions. They had the and aspect of being at the seminar and having increased sales. And that's how we got that 48. Then we divided that by, okay, the probability that they attended the seminar. Well, how many people attended the seminar? 80 out of the 100, right? Okay, so what we're really doing when we look at this and just looking at collectively the whole table. So I look, because we could do this a little bit different. Okay. Oh, I don't want to erase all that stuff. So we erase the green. All right. I could say, if I just look at the whole thing, if I have 48 people out of 100, that's how many people had increased sales and attended the seminar per those 100. Does that make sense? If I divide that by the people that attended the seminar, how many people attended the seminar? 80 out of the 100 people that work for me, right? Divide that by 100. Okay. Does anybody know how I do this division with a fraction divided by a fraction? You multiply by the reciprocal of that bottom one. So what happens is that the hundreds cancel out, and you're left with 48 out of 80, which is exactly that we got when we just focused on that first column, right? Does that kind of make sense? Okay. So that allows us to make the general formula right here, okay, which is called the conditional probability formula. And this is based off of probability that we've already done, okay? And I'll talk about it here in a moment. We'll run through a little bit of algebra in a moment with this formula and see the relationship. But it says for any two events A and B, so the probability of a B occurring, given that A has occurred already, okay, can be found by this formula. It says P of B, vertical bar A, okay, that vertical bar red is given that. A has already occurred equals probability of A and B divided by probability of A. Does that make sense? Probability of A cannot be 0, right? Probability A, why would probability A not be allowed to be 0? Yeah, you can't divide by 0, right? Okay, so what happens here, just think about this. Think yesterday. Did anybody have the question yesterday come across? I think, Jagger, I think you asked this. There was a question about marbles getting pulled out of a bag, and you kept one, right? Okay. Let's think about that. If I take, let's say we have 6 red marbles, 4 white ones, and let's just leave it at that. And I say I'm going to pick out one marble, probability of I pick out one marble and I keep it, okay, one red marble and I keep it, and then on the second pull, I get a red marble. So I'm looking for that situation, a red marble followed by a red marble. Does that make sense? Okay. Well, that probability, okay, on the first pull, how many marbles do I have to choose from? Okay, so on the first one, 6 red ones out of 10 total, right? Okay. If I get a red one on the first pull, I'm keeping it, putting it in my pocket. How many red ones then are you allowed to have in the second? 5 out of 9. Okay, that's how we do that. That's right there. This was conditional probability. Okay, that right there. And let's just think about this. Let's take this real quick. Let's go. If I multiply both sides by P of A, I get probability of B given A times P of A is equal to P of A and B. Okay. I'm going to rewrite this. I'm going to restructure this as P of A and B. Just use the symmetric property and flip these around. And do that. Okay. Now, I'm going to take the right-hand side and just rewrite this as probability of A times then the probability of B given A has already occurred. Okay, so think about what this is right here. Okay, and think about what that is. That right there is probability of getting a red and a red. Does that make sense? or a red, then a red. That's that right there. P of A is that right there. What's the probability of getting red? 6 out of 10, right? This here, then would be, okay, what's the probability of this second thing occurring, which they're calling B? This would have been, what's the probability of getting red, given that red has already occurred? It'd be that thing there. Does that make sense? So what I want you guys to understand is that this given that statement, or this conditional probability formula, comes from working with the multiplication rule of dependent probabilities. Okay? Is that okay with everybody? Does that make sense? So let's kind of talk about how we use this in some practice problems, some scenarios. So in a study designed to test the effectiveness of a new drug, half of the volunteers received the drug. The other half of the volunteers received a placebo. Okay? Do you guys know what a placebo is? What's a placebo? It's what? Huh? No, that's not it. Does anybody know what placebo is? It's medicine related. It's say again? Okay, it's a fake medicine. Okay, usually it's like a water pill or a sugar pill or something like that. Okay, because if I give you let's say you have an ailment. Okay, let's say you got a headache, and I give you a pill and I tell you it's Tylenol, but it's just water. Okay, but I told you it was Tylenol. Psychologically, okay, that can stimulate a response from your body physically, okay, chemically, that will alleviate the headache. Does that make sense? So the psychological impact of thinking that you're taking a medicine that will help you will actually create a chemical response that will help you. Does that make sense? So if I have a new medicine and I want to make sure that that new medicine is working, I'm going to give it to this side of the classroom. I'm going to give you guys the medicine, okay, the legit medicine. This side of the classroom, I'm going to give you the placebo. I'm going to tell you that it's the medicine, but it's a water pill. Does that make sense? And there's nothing that is going to chemically change you other than the thought that you're getting the medicine. Does that make sense? So your body, you might stimulate your own response. But because I have you guys as the group that's getting the real medicine, you guys are considered, the placebo is considered the control group. If there is a chemical response that the placebo generates in your body, I can use those data values to compare to the data values that I get from the people actually taking the real medicine. And if there's a difference, that difference then is attributed to the actual medicine and not your body chemically responding to that psychological impact. Does that make sense? So that's the purpose of a placebo, is basically to say, was it really the medicine that worked, or was it just my body and my mind thinking that I was getting medicine that was going to work? Okay. So that's what a placebo means. Okay, it's a tablet or pill containing no medication. Okay, so the probability of a volunteer receiving the drug and getting well was 45%. What is the probability of someone getting well given that he receives the drug? Okay, so when we do this, okay, think about the phrase that is being asked. I always go back to the question first before I even start trying to decipher values and all that kind of stuff. Okay, it says, what is the probability of someone getting well? So probability of getting well, and then it says, given that they receive the drug. Okay, so I'm going to rewrite this as probability of, I'm going to just say GW, given that they got the drug. Well, going back off of what we said earlier about what a given that statement is, okay, the way that we do that, and there's a pattern to the formula, the way I remember the pattern of the formula, is that it's always you take the two things that are in your given that statement, and you put the word "and" between them, and they become your numerator. The denominator, because it's kind of last right here in this side of the equation, it's the last thing that was over here in the probability event. Okay, so when I say getting well given that they received the drug, so this numerator is going to be probability of got well and received the drug divided by then the probability of this last part, D, probability that they got the drug. Once I set that up, now I'm just going to go run through the problem and see, did they tell me a value for somebody that got well and received the drug? Okay, so is there a statement of somebody that we had that? So it says the probability of a volunteer receiving the drug and getting well was 45%. Does that say exactly this right here? Received the drug and got well. So, and we also talked yesterday that, you know, this, when I say P of A and B, that can be reversed as the probability of B and A. Okay, it's kind of a two-way street there. So, received the drug and got well, 45%. So 0.45 is that numerator. Okay, and now it says, now I need the probability that they received the drug. It says, in a study designed to test the effectiveness of a new drug, half the volunteers received the drug. So if half received, what's this decimal down here? 0.5, right? So if I divide 0.45 divided by 0.5, that makes sense. It's 0.9 or 90%. And think about what that 90% means. I always think it's a good idea to go back and think, okay, now I got an answer. What does it really mean? Okay, it says probability of getting well given that you had been provided the drug, right? Getting well given that you were taking the new drug. That 90% says, okay, if we've got 6 people and I give them the drug, 90% of those 6 people are going to get better. Does that make sense? Okay. Where that 90% was never realized or explicit in the study. Okay, but we can run through these probability formulas to get that to appear. So the probability of a volunteer receiving a placebo and having his or her health improve was 20%. What is the conditional probability of a volunteer's health improving given that they received a placebo? Okay. So let's write that one down. So conditional probability of a volunteer's health improving, let's just say health with an arrow going up for improve, given that they received the placebo. Okay. Well, then the numerator is going to be probability of health improved and placebo divided then by the probability of receiving the placebo. Okay. So are we okay with that? As I run through the scenario, it says the probability of a volunteer receiving the placebo and, so I'm always looking for these words like and, because they're going to tell me that right there. It's going to tell me that's the event I'm looking for. And then if they give me data about that, whether they give me processed data like this 20% or they give me raw data, I know that that's going to be information for my numerator. So 0.2 is going to go there. Okay. Now, they don't give me the probability of placebo in this, but this is a continuation of the previous problem. And what percentage of volunteers received the placebo in the previous problem? 45. Sorry, it was 50%, wasn't it? I think it was 50. Because it said half, yeah. So half received that. So 0.5. So 0.2 divided by 0.5 ends up being 0.4. Okay, so 40% probability, okay, that health increased given that they received a placebo. So if you think about that, what that tells me is that 40% of people had a chemical reaction, a psychological reaction that kickstarted a chemical reaction in their body that made their health improve. Okay, we had 90%, okay, of people that were given a actual drug and their health improved. Does that make sense? So we see there that just receiving this scenario, receiving just a pill, not knowing whether it's active medication or not, does increase health. Okay, but I think we can see then that because the 90% is greater than the 40%, that the drug, there was a greater degree of effectiveness with the actual medication, right? Okay. So conditional probabilities are usually not reversible. It's not always 100% that they're not reversible, but overall, we're not going to say if probability of A given B does not equal the probability of B given A has already occurred. There might be some situations that happens, but it's not a universal fact. Okay. One of the questions that they ask occasionally on standardized tests is something like this here in a moment. I'll write it all down. It says probability of A, let's write this, probability of B given A is equal to the probability of B and A divided by probability of A. Okay, if I multiply by P of A, I get P of A times P of B given A is equal to probability of B and A. Okay, I'm going to readjust that. I'm going to put this over here on the left. Probability of, I'm going to B and A, I'm going to rewrite it as A intersect B. And this over here, I'm going to rewrite as probability of A times probability of B given A has occurred. Okay, if this is true, okay, then how can I write this? Let's say that, well, let me see something. I might have it written better already from this class. Yes. These three things, so a lot of times that we want to know, are events independent or are they dependent? Okay? These three things allow us to do that. Okay? We've just talked about the probability of A and B. If it is equal to probability A times the probability of B, okay, if that's true, okay, then the events are independent. Okay? So if I had, the idea was if I flip a coin and it lands heads and roll a dice and it lands a 3, what was that probability? It's 1/2 times 1/6, right? Okay? And because a coin flip and a roll of a dice, they do not impact each other. One does not cause the other or does not change the other. They are independent. Okay? This here says the probability of A given B. If you're able to realize that that is exactly the same thing as the probability of A, okay, then what that means to us is that the events were also independent there. Okay? So think about what that means. If we have probability of A given B, okay, that right there over P of B. That's what this right here means, correct? If that is equal to P of A, okay, which is just the probability of the first event, which means to me that this given that didn't matter. Does that make sense? Okay. If I have the probability of, flipping a coin and getting heads, given that I rolled a 3, and that is just 1/2, because that's the probability of getting heads, right? Does that make sense to everybody? Then that tells me that this given that of 3 didn't matter, and the events were independent. Okay? So if you can ever meet one of these 3 criteria, okay, you're able to decipher whether the events are independent or dependent. Okay? If you can't meet these 3, they're dependent. If you meet one of any of these 3, they are independent. Okay? So that might be something that we talk about here later on. I'll probably talk about that maybe a little bit more on Monday with some examples. But it's all predicated off this given that, this conditional probability concept. This next question says a pet owner, or in a survey of pet owners, 45% own a dog, 27% own a cat, 12% own both dog and cat. What's the conditional probability that a dog owner also owns a cat? What is the conditional probability that cat owner owns a dog? So here's the idea. So this first question says, what is the conditional probability that a dog owner also owns a cat? So if we change that, we convert that into probability notation. It looks like that. Now, here's the scenario. It's basically saying, okay, I go up to somebody's house that was in this survey, and I open the door, okay, and I see a dog, because that's what the given that is, right? So I know that this individual has a dog. The answer to this problem is going to tell me the chance that they have a cat also somewhere in the house. Does that make sense? With only being able to see that they have a dog. Is everybody okay with that idea? Just by surveying, do you have a dog? Do you have a cat? Do you have both? I can now narrow my focus, and once I know one thing about that person, I can now have a better idea about other aspects of that person. Okay, and think about this. It says in a survey of pet owners, 45% own a dog, 27% own a cat. Okay, so when I go up to this person's house and I see, let's phrase it. I go up to their house and I know nothing about them. I initially have a 27% chance that there's a cat inside that house. Does that make sense? Okay, but I open the door and I'm greeted by a dog. That 27% chance now changes. Does that make sense? And we're going to see what it changes to. So that's what given that or conditional probabilities allow us to do. Okay, so we're going to take the probability of people that own a cat and a dog, and we'll divide that by the probability of owning a dog. So what's the probability to own a cat and a dog? It's 12%, right? So 12% own both dog and cat. Probability to own a dog? 45. So now, if I go 0.12 divided by 0.45, okay, cat and dog divided by a dog is now 26.6%. Okay, so that's not, in this case, it's not a huge difference. Okay, but now that I saw, I went to their door, I knew that they were, my probability is initially 27% chance that there's going to be a cat in the house. I go to the door and I see a dog first. Now it drops to a 26.6% chance that there's a cat in there. Does that make sense? Yes. These percentages up here? It's because if in the survey, let's say I surveyed 100 people, 45 of them own a dog, 27 own a cat, 12 owned both. Okay, so the rest maybe answered I don't fit that category. I don't own either. But this 12 is also inside that 45. Does that make sense? And this 12 is also a component of that 27. So they logically that way would not add to 100 either. But I think the best way of seeing it is that there could be an alternative response of not having either. This is an example showing you that the reversing of conditional probabilities are not the same. So now I'd be looking at the probability of a dog and a cat on top, divided then by the probability of a cat on the bottom. And that's still a 0.12. Now I'm going to divide that by 0.27. And 0.12 divided by 0.27, that's the 44.4 repeating as a percentage. So the probability that I walk into somebody's house not knowing anything about them and that I'm going to see a dog from the survey was 45%. Okay? If I open the door and I see a cat now, that 45% drops to 44%. So yeah, that would give me 26.6 repeating percent as well. We'll come back. We'll just stop right there for now. On Monday, I want to continue talking about this because there are some visual ways or graphical ways that you might be able to answer conditional probability questions. But at the same time, we should then, once we can do it visually, seeing the sample, it's kind of just developing the sample space by like a graphical approach. We can then do the same work with the formula. We just realize and see that we get the same answers. So we'll work on that on Monday. I don't think we got 5 minutes left here, but I don't think there's enough time to get through all of that here. What's that? Oh, we got one? I forgot. Today's a full day. All right, since I already said that, let's do that. Let me open an assignment so you can start working on that. 13.6.